So this topic is about solar constant. We receive the light from sun. Sun is the natural resource of the light. So this white light, which gives us the brightness, the intensity of the light depends upon the season, the place, and where we are living, depending upon the altitude, depending upon the place, depending upon the season, time of the day also. Because as the earth is revolving around the sun, and we have the day and night due to the spinning of the earth, the rotation of the earth. So we have sunrise and sunset. During this time, the intensity of the sunlight changes. So in the afternoon, nearly about from 12 to 2 o'clock, we have maximum intensity of the sunlight. The amount of the solar energy, we receive the energy. This is the solar energy, what we receive from sunlight. So the energy, solar energy, received by the earth, we receive the sunlight, and by the earth, by unit surface area, unit area. If you calculate in SI system, 1 square meter, by 1 square meter area of the earth, in 1 minute. So how much energy is received by unit area of the earth in 1 minute, not in seconds, in 1 minute? This is called solar constant. Solar constant is the energy received by unit surface area of the earth at that given place in 1 minute. This value depends upon the place, as I said, and even depends on the time also. If you calculate this value, that is during the morning time, that is from maybe from 9 to 10 like that, and calculate the solar constant at the same place. So at a different time, that is at 12 o'clock like that. So it depends, because the sunlight, so when it strikes the ground, the angle at which it is makes with a vertical line is different at different timings and differs with the place also. So this solar constant, so it is generally denoted by S, and we can calculate this solar constant using an instrument called Angstrom pyrheliometer. So this is the pyrheliometer designed by Angstrom. So this is used to determine solar constant. Now I'll explain you how can we calculate solar constant using Angstrom pyrheliometer. So to design this Angstrom pyrheliometer, the main components we have here, we need 2 metal strips, and which are having same area, same surface area, made up with the same material, same dimensions, 2 metal strips with the same dimensions. We denote the 2 metal strips with the S1 and S2, and a thermocouple. A thermocouple, we know that it's a combination of 2 conductors or metal wires which are joined at the 2 ends, making 2 junctions, which is used to calculate the thermoelectric EMF and current also. A sheath, so to cover one of the strips and to protect the strip from the sunlight, a sheath and an electric circuit we need with a battery, rheostat and an ammeter. So these are the main components to construct the pyrheliometer, and let us have the construction of pyrheliometer. So this is the design of the pyrheliometer here. So these are the 2 metal strips. This is S1 and this is another metal strip S2. These 2 are made of same material and having the same dimensions. Only the difference is S1, one of the metal strips is directly exposed to the sunlight. So the sunlight directly incidents on the metal strip. It is exposed to the sunlight. And the second metal strip, this S2. It is protected from the sunlight by covering with a sheath here. So this is the sheath we denote with M here. So if you cover this metal strip S2 with this sheath, it is at a cold temperature, whereas this S1, as it is directly exposed to the sunlight, it is at a hot temperature, high temperature. So a thermocouple is connected in between these two metal strips here. So this is the thermocouple, and the two junctions of the thermocouple, one of the junction is connected to the S1, which is at high temperature, and the second junction is connected to S2 at low temperature. So due to the change in the temperature, and the galvanometer shows a deflection because an amount of the current is flowing through the thermocouple here. So this is the first arrangement. And the second arrangement is here we have an electric circuit. An electric circuit is to be connected to the second metal strip S2 here. So this is the electric metal here, electric circuit with a battery. This is the battery with a rheostat and a key and an voltmeter with an ammeter in series here. So this electric circuit consists of battery, rheostat, a plug key, voltmeter and ammeter here. This is connected to the strip S2, metal S2 here, just to compensate the current flowing through the galvanometer here. How does it work? So here we have two metal strips here. When it is the metal strip directly exposed to the sunlight, a metal strip, this is the metal strip S1, which is directly exposed to the sunlight. It is at a hot temperature. Whereas this S2, it is at cold temperature because it is protected with a sheath. And this thermocouple, two junctions are at two different temperatures, hot and cold. So we know that when the two junctions are at two extreme different temperatures, an amount of the current flows through thermocouple and galvanometer shows a deflection here. So this deflection in the galvanometer is noted. And this rheostat is adjusted until the current flowing through this circuit compensates this galvanometer. Until the galvanometer shows again zero deflection, we have to adjust the current in the electric circuit. So we have to move this rheostat till this galvanometer comes back to the zero deflection, and then we have to note down the value of voltmeter and ammeter here. So this is the experiment or the procedure how to calculate the potential difference in the circuit and the current here. So in this procedure, first we have to observe that it is directly, the S1 strip is directly exposed to the sunlight, and observe the deflection in the galvanometer and adjust the rheostat in the electric circuit until the galvanometer comes back to zero deflection. And then note down the value of voltage, voltmeter, and the current in ammeter. So those two values are noted here. Voltmeter reading is noted as V and current ammeter reading is noted as I here. Then electric energy which is calculated in terms of electricity voltage and current is V into I. In 1 minute, it is multiplied by 60 seconds, it is 1 into I here. And now here we have to calculate this electric intensity or energy in terms of the solar constant also. As we define this solar constant, it is the energy received by unit surface area. Here we are using the metal strips. So these are the metal strips. And area of the metal strip we denote with A. If this metal strip receives energy, the unit area of the metal strips energy receives the energy in 1 minute is equals to solar constant. I repeat once again, the solar energy received by unit area of the metal strip in 1 minute is equal to solar constant. Solar constant multiplied by area of the metal strip is equal to total solar energy received by the metal strip. So we multiply this solar constant with area of the metal strip, then you will have solar energy, total solar energy received by the metal strip. And here we have another term, absorption coefficient of the metal strip. It depends upon the nature of the metal, what metal we have chosen, alpha. So the total energy received by or absorbed by the metal strip S1, which is equals to solar constant multiplied by area of the plate and multiplied by absorption coefficient. So this is equal to, this is divided by 60 because we are calculating that in 1 minute here. This is equals to VI electrical energy. So yes, A alpha by 60 equals to here VI, S equals to solar constant VI into 60 divided by A alpha. And the units are joules per centimeter square per minute. Yeah. So this is the unit, SI unit of this, this is the unit of the solar constant. And this solar constant, as I said, it differs with time and the place. It is calculated at different places and it is calculated at different timings and then compared, and the graph is plotted for various values of S with respect to the time or the place here. The experiment is calculated and repeated for many times. And here we have the standard value, original value of S0. Actually, due to some that is absorption of the solar energy in the atmosphere, so the solar energy is not the correct value what we calculated experimentally. With the original value S0, how it is related, this is the expression here. The experimental value S equals to S0. This is the original value here. And this value, transmission coefficient tau to the power of secant z. So how much energy is transmitted through the atmosphere? Solar energy. How much energy is transmitted through the atmosphere by unit area of the atmosphere? Transmission coefficient whole to the power of secant z. What is this z? Z is the zenith angle. The angle made by the sunlight with a vertical line. So sunlight is coming in this direction. Sunlight is transmitted in this direction, received by the earth. This is the vertical line. So with the vertical line, so how much angle is made by the sunlight? This is called the zenith angle. It depends again with the time and the place. So we repeat the experiment and graph the values here with respect to z. Z value differs with the time. Secant z value is taken on x-axis and experimental log solar constant is on y-axis here. So you will have a straight line because this equation S equals to S0 out to the power of secant z. If you take logarithm on both sides, log S, this value equals to log S0 plus secant z tau. This is in the form of y equals to a plus mx plus c. So log S equals to log S0 plus secant z log tau here. Y equals to mx plus c here. So like that you will have this equation, an equation which represents the straight line. So S0 value is calculated from the graph. So S value, log S value and the log say secant Z value is plotted on the graph here. And y-intercept is equals to log S naught. This is equals to y-intercept log S naught value. And it is substituted here in this equation. And when you substitute this log S naught value for any given value of Z, we can calculate log S using this equation here, this one. So this is how we can calculate experimentally the solar constant, and the original value of the solar constant. True value is S naught equals to 1.937 calories per centimeter square per minute. How? How can we calculate this value? Using this graph only. We repeat the experiment for number of times at different timings in the same place, and we plot the graph between log S and secant Z. And if you have this intercept, y-intercept log S naught value, and taking the anti-log value for log S naught value will give us S naught equals to 1.937 calories per centimeters per minute. So this is how we calculate solar constant using this Angstrom pyrheliometer.